I know a reaction where the preferred solvent's a product. Methyl, primary, secondary, helps determine the reaction speed. The nucleophile comes attacks from the backside. Stereochemistry gets inverted when the halogen gets kicked out. There must be a good leaving group, but nothing comes close to iodine. No switch from R to S is fine. The nucleophile hits it from the back in no time. SN2 reactions of alkyl halide always attack from the backside. A concerted mechanism takes place. SN2. Rate law depends on concentrations of alkyl halides and the nucleophile. Both reactions matter for the rate. SN2. The nucleophile attacks the partial positive carbon. Attach the halogens because a nucleophile always attacks an electrophile. There must be a good leaving group, but nothing comes close to iodine. No switch from R to S is fine. The nucleophile hits it from the back in no time. SN2 reactions of alkyl halide always attack from the backside. A concerted mechanism takes place. SN2. Tertiary alkyl halides do not undergo SN2 reaction due to steric hindrance.
I mean, not perfect, but
That was pretty good.
So here we have an SN2 reaction, and so let's look at the components of the reactants first. So first we need a methyl primary or secondary alkyl halide, and here we have a primary alkyl halide. And also we have a good nucleophile and a good leaving group attached to the alkyl halide, as well as a aprotic polar solvent. So what happens in this mechanism is that the good nucleophile will attack the electrophilic carbon and cause a leaving group to leave. And so we see here in the transition state that the nucleophile attacks the electrophile and causes the leaving group to leave, and it occurs in the same plane as the leaving group. And so in this mechanism, due to backside attack, which is what occurs in this SN2 reaction, the stereochemistry inverts, causing, again, the wedges and dashes to flip. So here are some special cases where steric hindrance, which is super important for SN2 reactions, blocks an SN2 reaction from happening due to blocking of backside attack. Here's a tertiary alkyl halide, and so because of these three bulky methyl groups, the nucleophile is not able to attack from the backside. Also here is a primary alkyl halide with two alkyl beta substituents, and so again, the nucleophile is unable to attack from the backside because of these bulky methyl groups. Now when we look at chair conformations, here the halide is equatorial, and so in order for the nucleophile to attack from the back here, it has to cross through these axial bonds, which is very unfavorable, which is why in chair conformations, the halide leaving group must be axial. So again, just to reiterate now, the main requirements for SN2 reactions. The first is a good nucleophile, preferably with the formal negative charge. Second is a good leaving group. Third is a methyl primary or secondary alkyl halide. And third, the solvent, polar aprotic is optimal, and polar protic can also work. And importantly, tertiary alkyl halides cannot undergo SN2 reactions.